Okay, so first part of fluoroscopy, we're going to talk about conventional fluoroscopy. And when I say conventional, we're still getting digital images. It's not like we're talking about spot films that you may have heard of or actual cassettes being utilized. Most of it is still digital. But what makes this, in my mind, conventional is that we're still using this big, clunky image intensifier tube that we're going to go over in lots of detail and kind of reveal that mask and see what's electronics are hiding behind there. Lots of good stuff in there. Very similar in many ways to an X-ray tube. So you'll see some of the same language. Like, for instance, there's an anode and there's a cathode, and there are electrons that fly around, and there's heavy-duty kV that gets applied to the image intensifier tube, but we'll get to all that. What is fluoroscopy? Have you guys seen it at this point? Right? Or I've maybe not been involved, but seen some fluoro. We know that it's kind of like live-action X-ray, right? It's the ability to go beyond just these static images that we usually see and see something dynamic. So we're able to watch barium flow down someone's esophagus into their stomach. We're able to watch blood flow or contrast flow through a vessel if we're in angio. And fluoro is being used all over the place. It's being used, although I don't touch on it much, with the C-arm in the OR. And it's being used, as mentioned, for GI kind of work, but also there's a whole huge department based on cardiac catheterization and on special procedures that you might find yourself in one day. Right now, you get a rotation, well, next year, not as first-year students, through the special procedures angiographic departments to see what's going on in there. So they're heavy users of fluoro, right? And it's been around for a while, and I don't know if you know this, you think of this guy as the light bulb, right? But Thomas Edison created the fluoroscope, right? And as mentioned, the idea here is we get to observe anatomy that's in motion, and it can help locate anatomical structures. It's used in the OR, as mentioned, to kind of see where they just put a screw or kind of make adjustments if they need to. So it's really a good tool, although it is heavy on the radiation dose, right? So that is a downside. And it should be used minimally, right? We shouldn't be using it to position a hip, right, before we actually take a real X-ray. That's kind of like a no-no. I saw someone do that once. And they used a remote room to do it. So the monitor was outside. We'll talk about the couple of different types of rooms also. So yeah, 1896. Been around for a while. And what is our role in fluoroscopy? It's basically to assist, right? To prepare the room, get the barium ready, and as you may have seen, there's different types of barium depending on the procedure. If it is a barium enema, then we may be responsible for inserting the barium tip. We don't do that under fluoroscopic guidance, by the way. We just aim and hope for the best. But the reason why it's called image intensification, or the II tube, is because typically all of these procedures were done and was really, really dark because the image quality was not very bright. So to try to make things a little bit brighter, they would dim all the rooms. They'd use these like crazy glasses. And the idea now, besides being able to see these images in a dynamic kind of video way, is that we can save them digitally and they can be reviewed. And you can see the video as it's happening in the room, but most times there's a monitor outside of the room as well, so you don't have to be in the room. In the past, we had to be in the room. We had to wear our aprons. We stood behind the radiologist, and maybe I'm dating myself a little bit, and there was a lot of fluoro cases. You are in fluoro, for a few hours every morning. And usually it died down early afternoon or late morning. The idea for a lot of these procedures, though, is that patients couldn't eat. So you weren't doing much fluoro at 4 o'clock in the afternoon because that would make patients starve themselves. So these things were generally done earlier in the morning, and they just kind of skip breakfast. So here's an example of fluoroscopy being utilized in an angiographic suite. And this is kind of like a C-arm. It's really cool, but this picture actually belongs in the next lecture. Anyone know why?
To happen in operation.
No. What can you see that's basically in the middle of the image? Took a dart and went pretty much the middle of the image. What might you hit?
The intra-operation.
It's just to the right of the monitors, but it's actually closer. See this thing right here? Okay.
Yeah.
That's not our clunky image intensifier tube. That's a digital fluoroscopy tube. So it's square. Right. They basically work in a similar way, but the digital quality is better, of course. But we'll get to that when we get to it. So yeah, we're able to see the GI tract. We're able to see angios. They use it when they're putting stents into patients, when they're putting catheters. If you ever know anyone that's had an angioplasty where they put a balloon to open up a vessel, that's done under fluoroscopic guidance. Pacemakers are done under fluoroscopic guidance. So, I mean, these things are being used, right? Sometimes there's turf wars between the cardiology department and the x-ray department because there's a little bit of a crossover there. Sometimes they'll put an ultrasound probe on a catheter into a patient. So all sorts of interesting things. But yeah, there are cool monitors associated. And even studies done where the bigger monitors have actually made a difference in the prognosis to the patient. So that's a good segue to kind of talk a little bit about what's in a fluoroscopic suite or room. So we have some monitors. They're nice if they're flat. I actually remember big, giant, clunky monitors hanging from the ceiling, and I'm trying to remember if I was ever scared that the whole thing would just fall, because these monitors were gigantic. And they moved around, and luckily nothing ever happened. I think I'd be more scared now than I was then. So a lot of these rooms have a regular x-ray tube in it, but we move this thing to the side. We move it out of the way. In most GI work that we do, occasionally we move this tube back in front when it's time after the fluoroscopic procedure. Sometimes we do what's known as overheads. Has anyone seen some of the techs do some overheads? Right? But technically, a lot of that doesn't get done anymore because the radiologist can kind of see what they want, and because it's live, they can get just the perfect obliquity. You know, when we say Merrill's calls for an RAO, that's supposed to be what? 45 degrees? How do you know it's 45 degrees? You know, the radiologist can kind of actually move the patient. They'll wear their lead glove, or they'll instruct the patient to turn, stop, just when like the pyloric antrum opens or whatever they're looking for in just the right spot. So it's a great tool. It's kind of the x-ray before the x-ray. But then again, you know, you're moving the patient while the radiation is going. So there's a lot of radiation involved here. Before I get to some of the actual radiation numbers, let's go over the rest of the room. So where is the x-ray tube? It's not in here. This is the II tube that we'll talk about. That's the image intensifier tube. The actual x-ray tube is down on the bottom in a conventional room. And it's controlled by putting your hand up on a lever here and moving this apparatus around, which I'll demonstrate in the lab. Right? We have this very expensive fluoro room that I use for like a couple of hours a year, basically, for one lab. Well, the reason is, why expose yourself to radiation? So we don't really want to use it too much. So other parts here, some of them have a spot film cassette slot where you can put in a CR cassette, or we used to put in a regular X-ray cassette, and that would give you one static image. So you see the image on the console, on the monitors, and then if you wanted it, you clicked another button and you basically took an X-ray. But the radiologist was doing that. So we don't even have that anymore in our room. If you go in room, what used to be room 4, it's now room 1. If you go in that room, you'll see that this slot is there, but it's just kind of covered up. Right? You can't get anything in there. It's got some lead protective aprons in here. And other than that, it's all of these rooms have a foot pad in them because it's very common in a fluoroscopic procedure to turn the patient straight up in the air and put them at different angles. So you need a table that can go up like that. And there's a cassette tray, and that's basically for your regular procedures that you use. We have to move this all the way out of the way, as far down as they'll go, because, and it's happened to me, half a dozen times, where radiologists will start to fluoro, and they'll see like a dark black thing on the monitor. So not only are we exposing the patient, but we're wasting the physician's time, and they're usually not happy about that. And it was all because I didn't move the buffy tray over. It's like one little thing I forgot to do, let's say.
So you move the buffy tray to the other side of the
Yeah, you move it out of the way and lock it in place. So we have our image intensifier tube, which is in here. It's encased in plastic. We'll talk about that more in a minute. But the goal is to convert an X-ray image to a visible light image and intensify, amplify that light, which is why it's called an II, image intensifying tube. So this video is going to be sent a couple of different places. It's going to go to the monitors here, but it's also going to go to the computers. And I'll show you an image where there's like a mirror that splits the signal between monitors that might be inside, monitors that are outside, and then send that image to actually a digital to analog converter, turning it again into ones and zeros, so then we could then get it into the computer and do fancy things to it. So what's our technique? MA 0.5 to 5? That's like less than a finger, right? I mean, we don't even have that ability on our regular consoles. Our consoles start at what? MA station. I know you hardly ever, I'm not talking about Macs, MA stations. I know you have to go back a while. We have 100, a 200, maybe a 300 MA station. So the MA is super low on here, half of 1 to 5. KB is high, but where is this dose coming from then? If it's the time, right? We're not talking milliseconds and fractions of seconds, right? I don't know if I have it in this lecture, but you may have learned a little bit about this in protection, I hope, maybe. That there's a timer on this. There's an alarm that goes off after 5 minutes. Even if it didn't go off, let's say 3 minutes of fluoro is an enormous amount of time of radiation compared to a third of a second, let's say. Even that's a lot. So the exposure rate seems lower than it is in radiography, but it's not, because the exposure is higher because of length of exams. Right? And in the OR, sometimes they go crazy with this. Like I've hit the alarm 3 times in the OR. That's 15 minutes of fluoro during like an hour and a half procedure. So I'm not saying that, you're holding it for 15 minutes, but as it accumulates, yes.
So for conventional fluoro, we can say it's like low and long. I mean, if like the tube current is really low, which means it takes longer time.
Yeah, so the 2 current, which is what MA is, is very, very low, but the time is huge, right? So, I mean, if you multiply, let's say, what's 3 minutes in seconds? 180 seconds? So 180 times 5 is how much mass? That's a lot. Even if we don't do the multiplication, just 180 is a lot. I mean, if you do a knee at 8, that's like 18 knees. Just right there, without even multiplying by 5. And that's without doing more. That's only 3 minutes. That's before the alarm even is like, you know, you're doing a little bit too much signal. Right? So it can get much higher. But Alara, guys, we try to be as low as reasonably achievable, right? Benefits outweigh the risks, right? We try not to do fluoro on pregnant patients unless it's an emergency. Now, here's something interesting. Automatic brightness control, what's that about? If you are, for example, fluoroing and you're following barium as it goes from the esophagus into the stomach, by the time it gets to the stomach, all of a sudden you're in a much thicker area of the body. Are you the Flash? Can you run out and change the technique and use a little bit more radiation where it's thicker? No, maybe on TV. But this system, automatic brightness control, will on the fly or automatically adjust by altering MA and or KB to increase or decrease, right? As the machines get better and better, there's less lag, right? What you'll see sometimes is if the doctor moves the fluoroscope too quickly, the image will blur a little bit, right, until it adjusts. So this is really nifty, and every fluoro unit has it, or else you really wouldn't be able to use it unless you're just focused on one spot and didn't move anywhere, which is sometimes the case. But in most GIs, right, we start with the esophagus and then we go down. What fluoro procedures have you seen? Anyone see an esophagram, just esophagus?
Yep.
Anyone see any studies with the pathologist, speech pathologist?
Yeah.
Yes.
Where they'll give them crackers with barium and that sounds healthy, right? Applesauce with some barium if people are having problems swallowing. So a lot of different things they do with fluoro. So here's the fun stuff. The fluoroscopic tube or II tube kind of looks like a milk bottle, similar to an X-ray tube in that you have a cathode side where things start. So we start at the left and we move to the right, and then you have an anode area down here. And in particular, I tried to take an image that's not in your book, although the one in your book should look almost the same. Theory is that on the registry, you don't know who the artist is going to be. So you kind of have to know what these things are. Anyway, so you start off with X-rays, and they're going to go through several conversions, essentially. And the next few slides run you through those conversions. So where do we start? So image intensification tube is going to start with an X-ray image. It's going to convert it to a light image, actually then gets converted into an electronic image, then back to a light image. So it's a bunch of steps, right? All along the way, we're increasing the brightness. So Eventually, right, that light image at the end, so it's starting off with X-rays, ending with light, but there's a few conversions in between. That light is going to go to the video cameras, like I mentioned earlier, so that you can see the image in the room, so that you can see the image outside the room. But it also might go to a CCD, standing for Charged Coupled Device, CCD, which is going to get that information into the computer ultimately. So, number one, X-ray enters this cathode area, and this looks two-dimensional, but it's kind of like a milk bottle. It's round, right? So this is a circle kind of coming out of the wall, and then going back in, right? So it's kind of like a big cylinder, except it, narrows down at the end. So that X-ray hits a phosphor that we have labeled here in yellow, right? It's made out of cesium iodide, and it's a scintillator. You've heard this term before. And it will take an X-ray and turn it into wavelengths of light. Obviously, maybe I shouldn't say obviously, but the wavelengths of light are representative of the different absorption levels that the X-rays went through to begin with. So it's not just one wavelength of light, or else you get like one contrast. You don't want just a gray image or any one color. Right next to this thing, right, it doesn't even look like there's any space in between them. So sandwiched next to this is what's known as the photocathode, right? The photocathode, and I'm gonna go back and forth between that and, let's see if I can, oh look, I'm here. What do I want to do? I want to put this here. Well, I want to be able to flip back and forth, so I think I got it. Okay, so this second area that's sandwiched right next to what's known as the input phosphor is the photocathode. The photocathode is another phosphor, except it's not a scintillator. Right? Scintillators only take X-rays and turn it to light. This is going to take the light from the input phosphor and convert it into voltages, electrons. So it's made out of partial antimony, partial cesium. Right, so now, right after this, we have high energy electrons. But just like an X-ray tube, we need to take those electrons and push them across the tube. So we need some kV, which again will act as the potential difference. And just like X-ray, the cathode side of the tube has a sort of negative charge associated with it, and there's a positive charge on the anode side. So we need to accelerate those electrons towards the anode, towards the output end of the tube, towards another phosphor, actually. So this is the third phosphor, except this one, it's not the input phosphor, it's the output phosphor. So we're going to apply, just 25 kV. Doesn't sound like a lot, but when you write it out and you actually write 25,000, and you tell someone that's 25,000 volts when they're used to like 110 and you plug in your lamp, it's a lot. We use a lot of voltage in our daily activities, and we don't even really think too much about it. I use 50 kV on a hand. That's not even that much, right? Yes.
This is a material that takes whatever input phosphor gives it and gives it to an electron.
So far, this is where we're at. X-rays hit the input phosphor, turns it to light. That light almost immediately interacts with the photocathode, turning that light into electrical charges, electrons. Now, so we're still, at the beginning of the tube. By the way, there are a couple other little things in here, right? The diameter of the input phosphor. So this right here is adjustable, right? And that will play a role in magnification of the image, so we can have different magnification factors. During our lab, I'll show you those, right? And literally things get bigger or smaller on the monitor. It's not like astounding, but it's in there. There is an effect on dose when it comes to magnification, but we'll get to that in a minute. Well, hold on, because we'll run out of time. Let's move to the next step. So we have these electrons that were just produced after the light was converted by the photocathode, mixture of antimony and cesium, into electrons. So now we need to apply our potential difference, our kV, it's 25,000 volts, 25 to 30,000 volts, and zip those electrons across the tube. So, just to give you some statistics, right? Approximately each photon, if it was a 60 kV photon, is going to be converted to 200 electrons. And we never just have one X-ray photon, we have trillions and trillions, so we're going to have billions of trillions. Don't quote me on that. It's a lot of actual electrons, which then later on get turned into light again. Well, it's complicated, but it's memorization, like I said. It's just remembering the steps, remembering some phosphor names, remembering, a few different processes. Yes. Okay, so after we have electrons, that's where we kind of still are now. We have to shoot them across. So the electrons, the tube itself, image intensifier tube, gets 25 to 30,000 volts, which will accelerate those electrons across. But as they are moving across, at the same time, they are also being compressed, right? So that whole stream is going to get more and more narrow. And you can see that happening as depicted by these kind of dashed lines that kind of start to come together. And how does that happen? That happens by the electron optics or electrostatic lenses, which are depicted by these little dashes. But you see how they keep getting narrower and narrower? And what they will do, electrons are negatively charged, correct? Yeah. So these electrostatic lenses will have a positive charge associated with them. They'll kind of float that charge out, and that will act to push those electrons away. And as those electronic lenses, those electrostatic lenses, are built physically in the tube to become more and more narrow, it ends up tightening your stream. Kind of, yeah. Right? Now, by doing that, right, that action of narrowing is going to give us more brightness, which after all is the main goal. And that brightness is known as minification brightness. So it's brightness that's associated with minifying or narrowing that electron stream. Yeah, so this whole object is to brighten the image. Part of brightness is going to be based on what's known as minification. which is the literal narrowing of that electron beam by the positive charge dished out by the electrostatic lenses.
I need to take physics and magnification. We do experience like when we put the flashlight closer to the area looks smaller but a lot brighter. Does it mean the same thing with magnification?
Yes. Yeah, that's true. So, based on what I said, though, right, there's more than one way brightness is created. Right? Brightness is going to be created from two different processes happening. One is magnification that we just discussed, but the other, which is known as flux gain, is simply based on the fact that we start with an input phosphor that is very large in comparison. So if you allow me to go back, the diameter of the input phosphor, which I said could be adjustable, but it starts at like 6, can go to 9, 12, or 16 inches. So the diameter, and the reason why diameter is an important term is because this thing is round. And we'll get to the problems of round objects being transferred to flat, square screens. Can cause some artifacts that are at the end of this lecture. But the diameter of the input phosphor is much larger than the diameter of the output phosphor, right? So our electrons get narrowed. They're on the way to the output phosphor. They hit the output phosphor, most of them. The output phosphor is zinc cadmium sulfide. Yes, lots of terms to memorize. And those electrons, they hit the output phosphor, and they then again get turned into light, but much more light than what was created from the initial input phosphor, right? I mean, if it was the same, why bother turning them into electrons? You could have stopped right at the beginning. So it's X-ray to light to electrons back to light. And things keep getting ratcheted up as we go. So there's brightness created through magnification, which is the narrowing of the electron beam. And then there's brightness associated with what's known as flux gain, just between the difference in the diameter, much larger diameter of the input phosphor compared to the diameter of the output phosphor. See how small this is in comparison to this? Right? It's about an inch. And then we have our light. But the idea is lots and lots of light. And these things work so well now that we don't even have to turn the lights off anymore in the fluoro rooms. But all those fluoro rooms used to have dimmers, right? They probably still use a little bit of that, but you don't have to now. Right? Now, where does that light go? Okay, what happens here? Where does this light go? That light, that intensified image, goes into some fiber optic cables or optics to either a CCD or a CMOS camera. But essentially, it's going to go to images in the room on the monitors, images on the monitors outside the room, and to the computer.
What is CMOS camera?
CMOS, I'm not sure what CMOS stands for. CCD I know pretty well because we have CCDs in our cameras, in our digital cameras, and probably in our phones now, I guess. So here's another image of the same thing, except we have a repeat of what we saw before, But now we see some of the optics and what's going on here. So to run you through this, X-rays, they hit the input phosphor, which is adjustable and can change the magnification ultimately of the image, followed by the photocathode, which takes that light, again, turns it into voltages or electrical signals, electrons essentially. Those electrons have 25 to 30,000 volts potential difference applied to them. So they go shooting across. That's supposed to be an E, standing for electron. The electrostatic lenses are focusing electrodes. Get another way to call them. You can see they narrow the image down. And then you hit the output phosphor. Then in the last slide, we started talking a little bit about what happens there. So you see there's a mirror in here that will divert some of that signal to a camera on one side and a CCD on the other side, which is linked to an analog to digital converter, because we have to take light, which is an analog type of information. If you watched it, it sounds very familiar to what happens in the CR process, and convert it to ones and zeros. So there's an ADC in here. So for every photon, we're getting about 5,000 light photons. That's the amplification happening. That's pretty good. So I talked sort of about this already. I'm just kind of going over it in just a little bit more detail, right? But the brightness, or what's known as the total brightness, is going to be a combination of the minification gain, which we said is basically the difference between the diameter of the input phosphor over the diameter of the output phosphor. Well, that's wrong, isn't it? So we'll tidy that up in a minute. So that's going to give us somewhere between 35 and 80 times the brightness that we started with. You combine that with the flux gain. Okay, so this is the way to remember minification. When you think of minification, you think of something getting bigger and smaller. Right? So think about that as the input phosphor, which can change size, and the input phosphor is linked with the output phosphor. So that's minification gain. The other part of total brightness is based on what's known as the flux gain. And the flux gain is based on the difference between the number of input X-ray photons you have compared to the output light photons you end up with. And we just said it's like start with one photon, end up with 5,000 light photons. Yeah. One part.
Okay, so you're saying the minification is the input phosphor from someone else?
So the minification gain is the brightness that is achieved when you go from the large input phosphor to the smaller output phosphor. The flux gain that you get is based on all the different conversions that occur. Not simply the size of a phosphor, but what those phosphors do. So that's based on the ratio of X-ray photons that you start with compared to light photons that you end up with. Those two processes contribute to what's known as total brightness. Right? So total brightness is a combination of the minification gain times the flux gain. And overall, this will give us, anywhere between 5,000 and 20,000 light photons for every one X-ray photon. Now, I don't think I'm going to test you on the next part here, but there is a newer term that is replacing total brightness. Total brightness, that term, as the book describes, is being replaced by what's known as the conversion factor. Right? But it's essentially very similar, right? It takes into account the output phosphor versus the input phosphor, right? And it is based on brightness, which is what candela is a term for brightness, like that stems back to like how many candles would brighten up a room. Over time, but we're not going to go with this yet. Too new for me. We're going to stick with total brightness, which we said is the product of magnification gain and flux gain. Now, I alluded to the fact that the diameter of the input phosphor can change. It doesn't iris in and out, right? Like something out of, I don't know, sci-fi movie. But certain parts of the phosphor will be more active than others, or some will be turned on and some will be turned off. So the thing doesn't actually like shrink. But you can utilize fluoro in what's known as a magnification mode. Right? And it's inversed, kind of like the way CR is in our lab. Right? When the number goes down, the magnification increases. So when we go from let's say when we go from 9 to 6, we get more magnification. But look here in red. I only put important things in red usually, right? When we magnify the image, we get 2 to 4 times the dose. In other words, dose goes up. And any image intensifier that has the ability to do magnification is known as a multi-field or a dual field intensifier. And I don't think I've seen one that doesn't have this property. Even the C-arms can do this. Interestingly, and somewhat counterintuitive, because how often have we said that magnification is associated with a decrease in detail? But in fluoro, it's the opposite. At least you're getting something for the dose. In fluoro, when you magnify the image, the spatial resolution gets better. And the reality, and I didn't know this until a few years ago, was the actual diameter of the input phosphor, right, that big circle at the beginning. Like I said, its diameter doesn't change, but what allows you to go to what they call a different diameter, or sometimes a multi-field number, right? The ability to change from that 6 to 9 to 12 to 16 is going to occur by changing, so I thought this was interesting, changing the charge on the electrostatic lenses. So if we go back, right, actually changing the charge on these lenses will affect how wide or narrow that beam of electrons going across will be. So that's what is actually going to control magnification.
So magnification mode, they have advantage that like make better resolution, but disadvantage is increase the patient dose.
That's right. That's the way a lot of radiology is. Better images, more dose.
So geez, I hadn't written down magnification on dose.
So yes, right? Multi-field number down, going from 16 to 9 gives you magnification. Yeah. Automatic stabilization of brightness, basically the same as automatic brightness control. So if you see the term, they're basically synonymous. You see I didn't finish. Some of this you probably already know. Essentially, when we use heavy-duty barium, right, we're up in the 110, 100, 110 range. Things go a little bit lower if we're just using air. Even lower if we're using, it's not even, well, I guess it is kind of listed here. If you're using contrast media, like non-ionated contrast media, that can get burned out. So our KD levels are lower for that. You don't use 110 in an angiographic procedure. Which means even more dose when you think about it. So, does this system work perfectly? That's kind of where this slide starts. And we're going to get into, very briefly, just a few of the possible things that could go wrong in fluoro that will degrade your image. So first of all, just like X-ray, if you don't use enough radiation to begin with, you're not going to get a good image, right? So you still have to use a proper technique, right? You can't use just a few photons and expect everything to work out. Right? So it still needs to be a significant amount of radiation. So that's what they mean by no form of intensification is going to, you can't make a snowman out of one snowball. Right? You need enough snow. But there are some other issues that can go on besides not using enough radiation. So if you don't use enough radiation, you get noise. And you can see what happened here. If you provide the system with more signal, basically more data, because you use more radiation, see how it all kind of goes together, you get a better image. I don't know why this little thing keeps showing up here. All right, so here, I guess someone fluoroed a catheter, I think. And when you look at A, you could barely see anything. And the tubing, essentially, so this was just like thick plastic tubing, is seen much better going from A to D as the signal to noise ratio keeps increasing. So noise goes down and our image contrast gets better. So this doesn't always work perfectly, right, this system. That's why part 2, things work a lot better in the DR version, but image intensifiers are all over the place. Have you seen any of the C-arms parked? Have you seen any ones where the C-arm is square? Most of the C-arms are round and have that image intensifier. So that's older technology. So we're talking about pretty new stuff when it comes to digital fluoro. you're going to see more and more digital fluoro. They just haven't made it to the C-arms yet, but they're being installed in rooms. Everything always starts off more static and then goes mobile. What happens if some of the X-ray photons don't get absorbed, or if some of the photons go backwards and kind of bounce back off of the output phosphor and back into the system? So these are some things that can happen. Luckily, you know, if it's a small percentage, it doesn't really make that much difference. But it can happen, right? And the end result would be that your contrast would go down. But honestly, the fluoroscopic images that we utilize, the power is not really one image per se. The power is being able to see the flow. I was actually talking about this yesterday, related to something different, but if you had a heart valve, so a heart valve looks like a circle, right? And then you have blood flow. But if you look at it like this, don't go with the point of the pencil meaning anything, but is the blood flow going from ceiling to floor or floor to ceiling? Why? How do you know? No. You don't know. But if it's a video, then you see the blood either going up or down. And in a heart situation, in a cardiac study, if you have something like regurgitation where blood flows through, but some of it goes back, which is bad, right? You can't see that on a static image, but on a dynamic image, those are the kind of things that you can see, which could be really important to the patient. They might need surgery or new valve replacement. So one type of artifact or reduction in contrast, I don't know if we would strictly call it an artifact, but something that will cause your contrast to be reduced, which is overall not a good thing, right? Is known as pincushion distortion. And pincushion distortion is simply based on the mechanics of starting off with a light image that's symmetrical based on the input phosphor being round, but your output phosphor is square. It's basically like a one inch postage stamp. Right? I don't know if you get that from the picture here. Not really. It looks like it might be round, but this is not round. These are. Is everyone clear on that? Input phosphor is round, but the output phosphor is square. Hard to put round pegs into square holes, as they say. And that can cause a little bit of distortion. Some of that distortion is reduced when you use magnification mode. Honestly, I don't know if it's worth using certain magnification modes just to reduce pincushion a little bit, because after all, you're getting, you know, at least two times the dose when you use magnification mode, right? So I don't know if that trade-off is worthwhile. And magnification mode does just that. It magnifies the image. So if you didn't want, you're cutting some of the anatomy when you magnify other parts of the anatomy, right? Because you only have one monitor that's one size. So if you magnify anything on there, it's going to expand as much as the borders will allow on an image. Everything doesn't just get bigger. Veiling glare is something else that will reduce contrast. I really couldn't find a good image of this, but it's essentially caused by scattering of light within the X-ray tube. Just the way X-ray photons scatter, light photons scatter a little bit. And if you look at the very last sentence, little can be done to eliminate this issue. So it's just part of the process. Can't really do anything here. Last one, my favorite one, is called vignetting. And its appearance is that of losing some of the brightness level, or losing basically parts of your image at the periphery, so where my arrow is kind of moving around over here, at the output phosphor. And again, a part of this has to do with starting with a round diameter input phosphor and trying to capture all of that image onto a square output phosphor. So that's the hard stuff, which is just memorization. The rest of it is also memorization, but at least it's a little bit more visual. Right? What do the actual machines look like? Well, we already saw one of them. The description of what I showed you was a conventional room. The other type of room, which still uses an II tube, an image intensifier tube, so it's still conventional in theory. So I'm kind of using the word conventional for two different things, just to confuse you. There is a remote room. Anyone see a remote room? Where the fluoro is done from outside of the room, and you have like joysticks and stuff, and you know. But the main difference is that the image intensifier tube is, instead of on top, it's underneath, and the X-ray tube is on top, like we're kind of used to. Things are flipped around. Looks like this. Right, so down here you have all of your image intensifier. So conventional is what we're used to. Conventional is what we have here in the lab. We have a fluoroscopic unit on this carriage that moves around. You have to be in the room to operate it, right? You have to be wearing your apron. There's some lead sheets here to help protect you from some radiation. It's a little bit extra, but you have to be in the room basically to operate it. Whereas in a remote room, you can do everything from outside. So you have a series of microphones where you can talk to the patient, and you can tell them to oblique themselves. So the problem arises is if the patient can't do what you ask them to do, then you have to go in the room and position them anyway. Right? So if you have the patient that can kind of turn, and the physician can say, turn up a little bit higher, and the person can do it, then you're nice, really nice. Less radiation for you, right? Because you're not in the room. And you can move the table back and forth and do all this stuff from outside the room. Not so good if patient can't understand or just is unable to do what needs to be done. Right? Then you're kind of back to the drawing board anyway. That's really the only difference. It still comes under the definition of conventional fluoroscopy to me, right? Still using an intensifier tube, it's just in a different place, right? All those transitions that we talked about, that's all the same. It's just a different kind of operation. In terms of protection, right? And like we said, there's a lot of, how the sounds are broken. There's a lot of radiation not just to the patient, but to who is in there, which is why I do this lab once a year and throw on my apron and fluoro, because I don't want to be doing this all the time. So you have to have lead gloves if you're going to move the patient around to actually go beyond that, curtain of lead to actually, maybe take someone's hip or thigh and move them into a certain obliquity perhaps. Distance is not going to help you too much. As a tech, if you're in the room, and that's happening less often because we're not doing, spot fills. We used to, like I was kind of demonstrating before, but I don't know if I finished my little demonstration, is we used to have to hold these like 9x9 size cassettes. And when the doctor wanted a spot film, we'd actually hand them the cassette. They'd slip it in that slot, which I told you no longer exists really, and they'd take some x-rays, give it back to you, you'd stick it as far away as you could, somewhere on the side, grab another one and be ready for them to do another image. So distance for you though, you would be behind the radiologist. They're wearing your apron, they're wearing their apron, you're wearing your apron, everyone's wearing aprons is the point, and you maybe stand as far back as you can. But how far could you possibly be? You couldn't be like, oh, you need a spot? Toss the cassette. That doesn't really work. So radiologists are getting more radiation than radiographers. I know, right? Earn that extra zero in their paycheck each week. Of course, you know who's doing the fluoro now. RAs are doing the fluoro now. Radiologist assistants. That was the main reason for RAs. So they can do fluoroscopic procedures and radiologists could sit back and read images with their Starbucks coffee. I saw a video of a radiologist the other day on YouTube, and it was top 10 reasons I chose to go into radiology. And one of them was so I could sit back with my coffee. You can't do that when you're on rounds, right? The other was I don't have to talk to people. So there were some good rationales to it. And now, okay, where was I going with this? They don't even have to get as much radiation, including in angiographic procedures where it's just fluoro all day long, right? In the angiography suites, that's all they do all day. Is fluoro, fluoro, fluoro. There have been actual studies where radiologists that get brain cancer have cancer on the side closest to the tube more often than not. Yeah, crazy stuff. So we're almost done with this. Yay. Me too. Radiation levels, 2.2 R is what we don't want to exceed. I don't know if the room's shut off. I've never seen a room just say, stop, you're done. There's just that alarm that goes off after 5 minutes, and I've seen people hit that repeatedly. I don't know if we hit it a 5th time if it stops. Minimum source to skin distance, it's a little bit more lenient for mobile equipment like the C-arm. So C-arm says you can be 12 inches from the patient. That's pretty close, right? Where's our tube usually? 40 inches away. This is 12 inches away. Which means what? Inverse square law, more radiation. Much more radiation, because half of 40, 20 would be 4 times the radiation. This is almost 8 times the radiation. It's all for the benefit. Okay.
I'm always behind the wall with
Well, that's good. Can we collimate? By the way, you can collimate with these systems, right? You can collimate the image intensifier, and I'll show you how to do that. There's actually a couple of different types of collimation that can be done. And here are some numbers that I'm not going to hold you to. And I'm kind of not sure why HVL is here. Didn't we talk about HVL already? we still know what it is, right? It's the amount of filtration that reduces the intensity by half, which is where it gets its name from. And that's really all you need to know. Have you ever tried these gloves? They're really bulky, and once you have them on, you really can't do anything. Like, you put these gloves on and try to write your name with a pen. Not happening.
They don't even have those gloves.
They should. So the last bit of this is mobile fluoroscopy. And in preparation for this lecture, even though I've done it a few times, I always try to check out YouTube and update myself. There are some good videos on like how to use the C-arm. So if you Google that, you'll come up with a few people. And essentially, it's the same stuff, really. You have an X-ray tube on one side and a fluoroscopic image intensifier tube on the other. Or if you're really fancy, which we said none of you guys have seen it, this becomes square, right? And you have a digital fluoroscopic C-arm unit.
That maybe.
And I do talk about that digital stuff in the next lecture. But what's nice about the C-arm system is this thing moves all over the place.
Oh yeah.
Right? And you'll see it when you go to the OR, because you get a rotation in the OR as well. A lot of times they also use this for pain management. So you might see that in some of the radiology departments if they're doing that there. But you can switch from sort of an AP position to a lateral. And there are several different locks, and you can go in a lot of different places. But these are used in the OR, in special procedures. The special procedures room that we saw before was like a giant C-arm, right? Except sometimes they have two of them. So it's known as a biplane unit. So you can do like APs and laterals at the same time. Well, more radiation. Let's send radiation to the patient this way and this way at the same time. But then again, if someone's like snaking some catheter through me, I want them to be like getting all 360 angle on that thing, right? I've actually had this done when I had my incident in 2013. But I'm alive, so. Brain hemorrhage, awesome. Yeah. What happens when you yell at the kids? No, I'm just kidding. So like the middle of the night, I got this like stabbing pain. I had like a subarachnoid hemorrhage. Yeah. And I had an angio, but I don't really remember that much. It was kind of tricky though, because when they put the contrast into your brain, your visual cortex like changes, and like I saw all these colors. No, I knew I wasn't dying. It was pretty interesting. Even when I was in that situation, I could still think. So I got very lucky. But so these units are great because they move, right? And there's an art to that. So if you watch some of the videos, that's the one piece of equipment we don't have. Well, that is an MR and a CT, but we don't have a CR.
Those things are really good.
The wheels can turn, so you can go back and forth. There's a whole art to this, right? It's associated with monitors, usually that have like a last hold function. So you'll have an image here. The next time you fluoro, it'll move to the right and kind of stay there, and then get replaced every time you do something. There's a connection between these two that you don't see in this image, right? With a really big cable. And I got mad at one student once. I generally don't get really angry ever. But they had one half plugged in and the other half not, and then turned it on. Remember, we're talking about thousands and thousands of volts. So I was just like, turn it off. That was not good. Not good. You'll get to play with this. You might be able to play with it a little bit outside, because a lot of times they're in the hallway. But that does it for part one of fluoro. stay tuned this afternoon or next Monday. For part 2.
The machines come in later.